it is clear. Now I will assemble the all three terms and then just see that what is the final term. Okay, so this dp is equal to, let me write it down from the term 1. So the term 1 is minus rho dou v dou t dot dl, minus rho dou v dou t dot dl. What is term 2? Term 2 is this, minus rho half gradient of v square dot dl plus rho v cross vorticity vector dotted with dl. What is the third term? Minus rho g into dz. Okay, so the first term is this, second term is this, and third term is this. Up to this it should be clear. Now I will simplify this term once again, this particular term. Okay, so what will be this term? Can someone tell me? Let me write it down. So what is gradient of v square? It is dou x v square I cap plus dou y v square j cap plus dou z v square k cap. Is that right? There is nothing wrong in that. What is dl? Is equals to dx I plus dyj plus dzk. So what is this term dotted with this term? This term dotted with this term. What will be this? This is multiplied by this, this is multiplied by this, this is multiplied by this. So that means this gradient of v square dot dl will be dou v square dou x into dx plus dou v square dou y into dy plus dou v square dou z to dz. Can someone tell me what is this term? This is looks like what we wrote for the pressure initially, that dou p is equals to dou p, dp is equal to dou p dou x into dx plus dou p dou y into dy plus dou p dou z into dz. Okay, so what I can write for this? I can write simply d of v square. Is that right? Because that's the rule for the total derivatives in case of for the rule of partial derivatives. So the total derivatives I can write it in this way. So that means this minus rho into half gradient of v square dot dl is simply equal to minus rho half d of v square, but this d is the differential operator. Okay, now let me write the equation once again. So dou p is equal to minus rho dou v dou t dot dl minus rho half d of v square, okay, plus rho v cross zeta dot dl minus rho g into dz. Is that clear so far up to this point? Fine, right?
Yes.
Okay, great. So this particular equation is something which is the like a simplified form of the Euler's equation, okay, because I substituted dou p dou x, dou p dou y and dou p dou z from the Euler's equations itself, okay, and this particular equation is basically the general form of the Bernoulli's equation, okay. So the Bernoulli's equation which we are like familiar with is not the general form, it is a simplified form that I will show you that how like the general Bernoulli's equation which you know is not the original one, or like it's a simplified form. I'll go into the details of that simplified form and all, but before that let me write it in a different way. So it is dou p plus I will take this term from left hand side to right hand side, so it is rho half of d of v square plus rho z into dz, okay, plus rho dou v dou t into dl, okay, minus I am taking this term to that side, so it is minus rho v cross zeta dot dl is equals to 0. That means I took all the terms from the right hand side to the left hand side and I put it a 0 in the right hand side. So far there is nothing wrong in this, right? So it is dp plus half plus rho half dv square plus rho g dz plus rho dou v dou t dotted with dl vector minus rho v cross xi into dl vector, okay. So this is the general form of the Bernoulli's equation, okay. So what you so far know, that's not the so in class he taught about Bernoulli's equation, right? In the second class if you see he discussed about Bernoulli's equation, I guess. Yes, anyway, fine. Okay, so far it is the Bernoulli's equation without any assumption, okay. This particular equation is the general form of the Bernoulli's equation without any assumption. So far this is clear, right? Now assumption, I will now make different assumptions and show that how you can get the familiar form of the Bernoulli's equation. Let's assume different terms now. Assumptions. Okay. Let's say that the flow is steady. So which term of this equation will be 0 for the steady flow? Can someone tell me which term of this equation which I boxed will be 0 for the steady flow? So steady flow means there is no like flow variables are not changing with time. Okay. So when the flow variables are not changing with time, that means this dou v dou t term will be equal to 0. Okay. This is one thing. Assumption number 2. So in the first case I saw that I assume that the flow is steady. Now I am saying, so again there is an interesting fact about this term which I should say in details, is that let's say this particular term is a very interesting term. Okay. So it says that it is v cross xi, that means velocity vector crossed with the vorticity vector and then dotted with the elemental line vector. So what are the situations when this term will be 0? This term will be 0 if this vector and this vector are when the dot product will be the two vector is 0. When they are perpendicular to each other. Am I right? Cos 90. So when the velocity vector crossed with the vorticity vector, let's say this vector is some vector a, so it is a and then this is dl. So when this a dot dl will be 0, that means physically when this velocity vector is the velocity vector crossed with the vorticity vector and then dotted with the elemental line vector is 0, or this a vector is perpendicular to this dl vector, then this term will be 0. That is the one condition. The other condition is when this v and dl, so the line which I essentially discussed about, that this line from line 1 to 2. So what is the definition of a streamline? That if you draw tangent at any point in the streamline, it will represent the velocity field, right? It will represent the direction of the velocity. So the other thing is when this v vector and dl vector are parallel to each other, right? That means when this dl is a streamline, that means if you draw a tangent at any point on the line dl, it will represent the velocity vector. In that case also this entire term will be 0. Okay. So there are two cases when this v cross the velocity vector crossed with the vorticity vector and that vector is dotted with elemental line vector is 0. That is a case. Second case is when that line which I am essentially draw, the line which I initially started with is a streamline. In that case also it will be 0. And the third simple case is when this xi is equals to 0. Okay. The third simple case is when this xi is equals to 0. That means there is no vorticity in the, like the vorticity is 0. That means the flow is irrotational. That I think you will you will know that later in this course. Okay, so when the flow is a irrotational flow, fine. So for these three circumstances, this particular term is rho into this complicated term which is appearing in the Bernoulli's equation is 0, and for the steady flow this dou v dou t term is 0. So then, like, what is the equation finally? If I drop this term, and also if I drop this term, then what is the final equation I am getting? It is dp plus rho half dv square plus rho g into dz is equal to 0. Am I right? Fine, right? Now I can write it as dp by rho plus half d of v square plus g into dz is equals to 0. Fine. Okay, so when this equation is valid, so this is the general, like the familiar form of the Bernoulli's equation which you know that, right? This is the Bernoulli's equation, that p by rho plus half v square plus zz is equals to 0. That is the familiar form of the Bernoulli's equation, you know, right? So that equation came after a lot of assumptions, that it's a steady flow and it's an that this equation is valid along a streamline. That is a very important term, because this v vector should be parallel to the dl vector. Then only this complicated term, this v cross, like the velocity crossed with vorticity dot dl, will be 0 when dl is a streamline. Okay, so that means this particular equation is valid along a streamline. But now, under what condition this particular equation will be valid between any two points in the flow field? Can someone tell? When this xi is equals to 0, when, like, if the flow is irrotational flow. So keep in mind very carefully that when the flow is irrotational flow, the Bernoulli's equation is valid for any two point in the flow field. Okay, but when the flow is not irrotational flow, in that case the Bernoulli's equation is valid only along a streamline. Okay, like, okay, when I am saying about the Bernoulli's equation, I am saying only this familiar form with the Bernoulli's equation. Okay, not with the general form. So these two things are very important. Okay, now if I integrate it, integrate 1 to 2, that means from, as I start, like which I started with, that from point 1 to point 2, the difference between the pressure is P2 minus P1, right? So it is dP by rho plus half integration d of v square 1 to 2 plus integration 1 to 2 d into dz is equal to, what will be this term? Constant, right? So for now, this particular equation is valid for both compressible and incompressible flow. There is no difference. Okay, like the Bernoulli's equation for compressible and the incompressible flow is the same. But for incompressible flow, rho is equal to constant, right? So I can take this rho out of this integral in the first term. So that means it is 1 by rho integration 1 to 2 dp plus half integration 1 to 2 d of v square, and also I am assuming that the gravity is constant, 1 to 2 dz is equal to constant. So what will be that term finally? 1 by rho p2 minus p1 plus half, it will be p2 square minus v1 square plus g into z2 minus z1 is equal to constant, right? So what is the familiar form which you know? That is p2 by rho plus half v2 square plus g into z2 is equal to p1 by rho plus half v1 square plus g into z1 is equal to constant. And this first term is called the pressure head, sorry, p2 by rho g actually I should write. So if I divide it by z once again, so it is p2 by rho z. So I will write it in a different sense now. So that means what I am getting essentially is p by rho z plus 1 by 2z into v square plus z is equal to constant. This term is called the pressure head. This is called the velocity head. And this is called the potential energy head or the potential head. Okay, in a different sense you can say, like from the concept of conservation of energy which sir taught in a lecture, that is the total energy is conserved, total mechanical energy is conserved. Okay, that also you can say. So this is the mechanical, like the kinetic energy term, this is the potential energy term, and this is energy related to pressure. Okay, so summation of these three is constant. That's what you can say, that this simplified Bernoulli's equation is also the conservation of energy. Okay, but this is coming after a lot of assumption that you need to say. So what are the assumptions? Let me write it down, all the assumptions once again, because this is important. So the Bernoulli's equation which we are familiar with, it's a very simplified form, but we don't know, but we have to know the original equation, like the original Bernoulli's equation, which is not that simple. So what are the assumptions? The very first assumption which you need to write, okay, what is the assumption, like what is the assumption for the Euler's equation? Like in the Euler equation, the flow is inviscid, okay, or the flow is frictionless. That means the term which is related to the viscosity in the governing equation should be 0. So that means the first assumption is the flow is inviscid. Sorry. What is the second assumption? That the rho is constant. The second assumption that flow is a steady flow. That's what that dou v dou t term is 0. The third assumption is that equation is valid. Like the Bernoulli's equation is valid along a streamline when xi is not equal to 0 and what is xi? Xi is the vorticity, that is for the irrotational flow, like when the flow is not irrotational. Bernoulli's equation is valid between any two points in the flow field when this vorticity vector is 0. What is the assumption number 5? That it is incompressible flow. Like for this particular form, okay, again you need to remember it once again, that I am writing all these assumptions for this particular form, like for the familiar form. Or let me just skip it, I don't need to write it. So these are the 4 things. So far, if you have any question, please tell me. I hope that now, at least like at the end of the course, you should know that what the Bernoulli's equation is all about. It is not as simple as that. It is a complicated form that you need to remember, and particularly you need to remember the assumptions which you made to arrive at this particular form. Okay, that the flow is inviscid, that means there is no viscous effect, and then the flow is steady, you assumed, and then the Bernoulli's equation is valid along a streamline when the flow is a rotational flow, or when the flow is not a irrotational flow. But for a irrotational flow, it is valid for any 2 points in the flow field. Okay, now I will be happy to take questions so far. If you have any question, you can ask me.
Sir, actually, I was not able to attend the last lecture, last live session.
Yeah, that will be available in the YouTube, right? Like they have not shared the YouTube link with you?
No, sir.
Okay, so hopefully they will share. Okay, hopefully they will share it in probably in few days. It will share.
Okay, sir.
Okay, the
Sir, and the
recording.
recording of this class also they will share.
Yes, definitely. The recording and this, like everything, like whatever I wrote, everything, this PDF also I will share.
Okay, sir.
Okay, so you don't need to write it down. You just need to understand. That's all.
Okay, sir.
Okay, so can I go ahead and so for the first week assignment, if you have any question for the first week assignment, you can ask me now, or else I can write down I can solve a simple problem for the pipe flow, which is probably in this week course the professor is teaching, right? The Navier-Stokes
Yes, sir.
equation for cylindrical coordinate system.
Yeah.
So what you want me to do? If you have any questions, you can ask me either, or I can go ahead and like demonstrate you how to solve the Navier-Stokes equation for a fully developed pipe flow. So this week assignment I can't discuss now because you have to submit it, right? What is this week assignment? There is a lot of. Are you able to see my screen? Hello?
Yeah, the assumptions screen is shared right now.
Okay, assumption screen is set. Okay, fine. Understood. Okay. So in this week you have a lot of things, right? So week 2 assignment, uh, what is the deadline? 8th October.
Sir, week
Sorry,
2 is
8th
10th.
August. Hello?
Sir, it is 10th, I guess.
Okay, 10th August. Okay. Sorry, yeah. And for the week 1, it is done?
Week 1 also it is 10th August. I think.
Oh, how it can be? Both of them are 10th. Okay. So the week 1 assignment you already did, right? All of you. I hope like once you submit the assignment, then only I can discuss about the solution. Now also I can discuss if you have some doubt or something. Okay, or else I can directly go to the derivation for the pipe flow, like deriving the velocity profile for pipe flow. So what do you want me to do? Hmm? Can someone tell? Okay, if you have any questions so far, you can tell.
Sir, we'll have in next class.
Okay. Then I'll stop it here, and in the next class you can the first you can ask. So I will hope that the concepts which I am giving is absolutely clear to everyone, right? Because the general lectures which are there in that YouTube, or like which will be shared with you for this course, like which are giving by professor, you need to follow it very carefully. Here in these live sessions I will, like, the objective is to clear your doubts if you have, and give some little detailed insight. Okay, so I hope it is okay with all of you, right?
Yes, sir.
Okay, so once again, if you have any questions so far, like the topic, like which is discussed so far in this course, you can ask, and if you don't have any question, we can meet in the next class.
Sir, do we have any WhatsApp group or something?
WhatsApp group? No, I don't think we have WhatsApp group. Did they share any link for the WhatsApp like WhatsApp group
No,
or
sir,
something?
they
No,
haven't
right?
anything.
Yeah, I think you can ask question in that forum, question answers.
Yeah, that form is there. Yeah.
That forum is there, right? So you can ask their questions, and also I just share my email ID. If you have any question, you can share it. And just in the chat box, I am writing my email ID. If you have any kind of confusion or question, you can write a mail to me. Okay, I have shared my mail ID. Okay.
Okay, sir.
Okay, then again we will meet in the next Saturday. In between, if you have any question related to assignment 1, assignment 2, any confusion, you ask me that first, and then I will move ahead with the new concepts. Okay.
Okay, sir.
Okay then. Bye.